4.3a Trigonometric Ratios. Using the unit circle, we can find cos theta and sine theta. Cos theta is adjacent, which is our x value of any coordinate on the unit circle, divided by the hypotenuse. And since the hypotenuse is just 1, then our cos theta is just equal to x. Our sine theta is just equal to y. So every point on the unit circle can be expressed as cos theta for the x value of the coordinate and sine theta for the y value of the coordinate. And that's why in the last section we found the exact values of coordinates on the unit circle. They're going to turn into the exact values for sine theta and cos theta. Now we can find the exact trigonometric values for all 6 trig ratios. 6? Yeah! So we have 3 more that we need to introduce. Cosecant, which is 1 over sine. Secant, which is 1 over cos. And cotangent, which is 1 over tan. This cotangent is easy to remember because it just has tangent in the name. But cosecant and secant may be forgettable. So I use cosecant can't be cos to help me remember that it's sine. We have an unfortunate class of notations. We have sine inverse, and that's where we're doing the inverse function to isolate for theta. And we write it like this. We write it in this, after the sine, we write a -1 in exponent position. And of course we have this, 2 to the -1, which means the reciprocal. So if you wanted to do the reciprocal, use big brackets around the whole sine function and show it as a reciprocal. And then that equals 1 over sine theta, and that equals cosecant theta. For the rest of the exponents, though, if we wanted to say sine theta all squared, we would put the squared sign right beside the sine. So when we see a -1 beside the sine, usually that means inverse, but that's also where all the rest of the exponents are going to be. So this is sine squared theta, means we're squaring the whole sine function. It does not equal this. Don't write this. This is too ambiguous. Then the squared usually applies to only the thing inside the bracket, but this isn't really bracket. It's already being controlled by sine, so this is just a mess, so do not write this. Example 1, we want to find the exact values for all of these trigonometric ratios for pi over 6. So pi over 6 is our angle in standard position. We want to see where this terminal arm of this angle in standard position intersects the unit circle. This point where it intersects will be cos theta, sine theta. If we can find that point, then we've just found cos theta and sine theta. Remember, we're using the unit circle, so the hypotenuse is the same as the radius, 1. And the angles here, pi over 3, pi over 4, pi over 6, or 60 degrees, 45 degrees, and 30 degrees, follow this pattern. 1, 2, 3, 1, 2, 3. Take the square root and divide by 2. And that gives us our sine theta is 1/2. Our cos theta, or cos pi over 6, is √3 over 2. And then tan is opposite over adjacent, so y over x, or sine over cos. So 1/2 divided by √3 over 2. The divided by 2's cancel, top and bottom, we're just left with 1 over √3. These are the reciprocal functions. 1 over 1/2 is just 2, or the reciprocal of 1/2. The reciprocal of this, 2 over root 3. And the reciprocal of 1 over root 3 is just root 3. There are the exact values for all the trigonometric functions for pi over 6. Now sine pi over 6 is easy to get on the calculator. If you type it in, you'll just get 0.5 or 1/2. And most calculators don't have these functions because they are just the reciprocals of these. This one's a bit harder though. If we type cos pi over 6 in our calculator, we get this mess. But if we compare root 3 over 2 with it, we do see that they're the same. Now what do you do if you completely forget what cos pi over 6 is and you get this decimal and you need the exact value? Well, there is something we could do. We could play with this number here, 0.866. Take all of this, including the decimals you can't see, and square it. And what you'll get is 3 over 4. Now from this, it's not 3 over 4, but from this we can figure out what it should have been. If we square it, to get back to the original, we need to square root it. So that means that it's really like this. And if we square root it, simplify that, we get the root 3 over 2. So we can actually determine these using our calculator and a few math tricks. We want to find the exact trigonometric values for all of these. So sine pi over 3, I'm going to use the unit circle to find the exact values. There are other methods. We'll be going through another method later on. Pi over 3 is 60 degrees. So here's our angles. There's 60, 45, and 30. And the coordinates go 1, 2, 3, 1, 2, 3. And then remember we square root and divide by 2. And we're looking for sine is the second one. So it's this here, root 3 over 2. Cos 7 pi over 6. We can count up by sixths, so 1/6, 2/6, 3/6, 4/6, 5/6, and 6/6. And 7/6 is the next one here. It's got a reference angle of pi over 6, or 30 degrees. And starting from the y-axis, it goes 1, 2, 3, always with the x's first, and then 1, 2, 3. And we're doing this one here, so we take the square root, divide by 2. And this is negative, so all these ones are negative. And we're looking for this negative root 3 over 2. Next one, tan 7 pi over 4. So we can count by quarters, 1/4, 2/4, 3/4, 4/4, 5/4, 6/4, and 7/4 is right here. Fourths are easy because they're always root 2 over 2, and we just need to figure out if it's negative or positive. So it's root 2 over 2, negative root 2 over 2. And so this one is tan. So tan is opposite over adjacent, or y over x. So negative root 2 over 2 divided by root 2 over 2 is negative 1. Next, sine 2/3. So there is 1/3 and there's 2/3 over here. Or you could convert these, if you have trouble with radians, you could convert this into degrees and get 120 degrees and then work with that. This one, starting from the y-axis, 1, 2, 3, coming back up, 1, 2, 3. We're doing sine, so we're interested in the y-coordinate, the y value of this coordinate. So root 3 over 2. And last one, tan, last one on this column, tan 5 pi over 3. Let's go 5 pi over 3. So 1 pi over 3, 2 pi over 3, 3 pi over 3, 4 pi over 3, and 5 pi over 3. I didn't fill this one out, so I guess I can do 1, 2, 3, 1, 2, 3. X is positive because we're over here on the positive x-axis, and y is negative because we're down here on the negative y-axis. And it's tan, so negative root 3 over 2 divided by 1/2. So the divided by 2's cancel. We're just left with negative root 3. But we got cos, negative 13 pi over 6. Now negative 12 pi over 6 is one full rotation backwards or clockwise. And negative 13 would be just one more sixth pi beyond that. We could also count it, where these are your sixth lines, and these are your quarter lines, so ignore them. So negative 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we're at negative 12 pi over 6. Negative 13 pi over 6 is right here. We want cos, so that's the x-coordinate. So that'll be this one here, root 3 over 2. Next one is tan of negative 54 pi over 3. Now I don't want to count that high, so let's see what we can do with that number. Tan, what's 54 divided by 3? Negative 18 pi. Now negative 18 pi is going clockwise, and remember every negative 2 pi is a full rotation. So this is negative 18 divided by 2 is 9 rotations clockwise. So we're actually going to end up with the terminal arm on the positive x-axis. This point here is 1, 0, and so tan is opposite over adjacent, or y over x, or sine over cos. So 0 over 1, which is 0. The last one on this page is sine negative 17 pi over 3. Now some people like to subtract off full rotations to simplify it that way. Subtract or add full rotations. We can count this one back by thirds. Negative 17 pi over 3 is negative 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. So negative 17 pi over 6 has a reference angle of pi over 3 or 60 degrees. And we were looking for sine, and so it's this y coordinate of this point, root 3 over 2. Example 3. We're given 2 points. One of these points lie on the unit circle. We want to find out which one it is and find the exact values for all 6 of its trigonometric ratios. Now the unit circle has a radius of 1, so that would mean that this point here, where it intersects the positive x-axis, is 1, 0. We can take these points and see if we can approximate where they are. 2 times root 2 is something just less than 3, divided by 3 is just less than 1, so we're over here. Negative 1/3 for our y would be down here. So I'm not too sure. It's in this area anyways, but I don't know where exactly it is. Let's see if we can do any better with the second point. 1/3 for our x value is about here, and root 2 over 3 for our y value is just under half, so about here. Now that one does not look like it's on the unit circle. So just a quick visual inspection, this one looks like it is and this one looks like it isn't, but that's not good enough. We need to be confident. So if we created a triangle here, going back to the x-axis, we could create a right triangle for both of these. And then we could use the Pythagorean theorem, a squared, because this side length here is 2 times root 2 over 3. This side length is negative 1/3, and this side length should be 1. 2 times root 2 over 3 squared plus negative 1/3 squared should equal 1 squared. This one equals 8/9. This one 1/9. And that does add up to 1. So this does fit on the unit circle. The other one, well, let's give it a try. 1/3 squared plus root 2 over 3 squared should equal 1 squared. And this is 1/9. And this is 2/9. So that adds up to 3/9 or 1/3. That does not equal 1. So we know that this one is not on the unit circle, and it doesn't look like it is visually either. So this is our point here, and now we want to find its trig ratios. Remember, sine is the y value of the coordinate, so negative 1/3. Cos is the x value of the point, so 2 root 2 over 3. And tan is opposite over adjacent, or sine over cos. So sine over cos. And when we simplify this, we get negative 1 over 2 root 2. Next is our cosecant, which just means it's the reciprocal of this value here. So it's negative 3. This one, the reciprocal for secant, 3 over 2 root 2. And the reciprocal of this is just negative 2 root 2. Notice that we never found theta, and we don't need to find the trig ratios. Example 4, find all the other trig ratios if we're given that cos theta equals negative 3 over 5. So cos, remember, is adjacent over hypotenuse. So I can draw something like that. If the adjacent is negative 3, that would be back here. So this side should be negative 3. And my hypotenuse is 5. Hypotenuse would always be positive, or the radius of our circle would always be positive. So could be 5 here, but it could also be 5 down here. If you remember the cast rule, cos is negative here and here. So we have two options, or two triangles going on here. This is 5 either way. So in quadrant 2 and in quadrant 3. Either way, we need to know this opposite side. So let's find that using the Pythagorean theorem. A squared plus b squared equals c squared, or negative 3 squared plus b squared equals 5 squared. This would be 9 plus b squared equals 25. And b squared equals 16. So b equals plus or minus 4. And this makes a lot of sense. When we take the square root of a variable square, we get plus or minus. This one's plus, and this one's minus. So this also gives us a clue that we've got two different options going on here. Now all the trig ratios, so sine, we have cos, so I'll skip to tan, and then on to the reciprocal trig ratios, so cosecant, secant, and cotangent. Now for quadrant 2, use these three numbers here. So sine would be opposite over hypotenuse, or 4 over 5. Tan, opposite over adjacent. Cosecant, It's the reciprocal of that one. Secant is the reciprocal of cos, so it's the reciprocal of this one that was given in the question. And cotangent is the reciprocal of tan, so the reciprocal of that one. Now for quadrant 3. So this is 2, this is 3 down here. Doing the same thing, just using the -4 instead of the +4. So the only change here would be using the -4 is -4/5. Tan, -4/-3, that becomes +4/3. Cosecant is the reciprocal of this one, so it's just going to be negative instead of positive like this. Secant will be exactly the same because we're taking the reciprocal of this, which is the same for both of these. And cotangent is the reciprocal of this, 3/4. Now, some of you might be thinking, yeah, but this isn't even on the unit circle. And I did that because I didn't want to work with fractions. But we could put it on the unit circle, not a problem. We could just say that if we have cos theta equals -3/5, that could be our x value of our coordinate. And then when we did our Pythagorean theorem here, we could do -3/5² plus b squared, and then we try to equal our unit circle radius, which is 1². And this would still work out. I just didn't want to do it this way because I didn't want to work with fractions. But it would definitely work. Example 5, we want to find these in exact values. And some people don't like to use the unit circle. So there is another method we'll go over, and that is just to use the first quadrant for everything. So you can find the reference angle, which should be from 0 to 90 degrees, or 0 to pi/2. It's the angle between the terminal arm and the nearest x-axis. Remember, you always go running back to your x. You find the exact value for that reference angle, and then determine if it's supposed to be positive or negative from the quadrant that it's in. So using the cast rule, for instance. So for the first one, let's see where this angle is. Cos 315 degrees is about here. Quadrant 4. Now we know that the reference angle for that is 45 degrees. So this actually equals cos 45 degrees. And I've just left a space here because we need to see if it's negative or positive. So we can use the cast rule, CAST, and that shows us that cos is positive here. Also, we can just say, well, cos is our x values of our coordinates, and we're on the positive x-axis, so quadrant 1 and 4 will be positive. Either way, this is positive. We can move on. Cos 45 is just √2/2, and we're done. Cosecant. Let's find that angle. -4π/3. Starting here, going clockwise this time is -3π/3, and one more is -4π/3. Something like that. Now that means the reference angle here is π/3. So we could rewrite this as cosecant π/3. Now cosecant, remember, is sine. Cosecant can't be cos, so it's sine. We look at our cast rule again, and we see that sine is positive here, so positive. Next, we're going to take the reciprocal. Do not take the reciprocal of what's inside. You're taking the reciprocal of the cosecant, so it's 1/sine. So somehow make yourself a note that the angle doesn't change. Because that's the most common mistake I see, is taking the reciprocal of what's inside of here. All right, now sine pi over 3. Pi over 3 is in quadrant 1. And so we can just memorize quadrant 1 and get this is 1 over, and this would be root 3 over 2. And I could clean that up a bit. I don't want a triple-decker fraction here. 2 over root 3. And last one on this page, tan pi over 2. Now tan of pi over 2, tan is actually just sine pi over 2, cos pi over 2. And pi over 2 is 90 degrees. It's right here. So the coordinates of this would be 0, 1. 0 is our cos, 1 is our sine. And we realize that we cannot do this. In fact, I'll write this in quotations because I don't want to leave it there as if it could exist. This is undefined because we cannot divide by 0. Example 6. Find the approximate coordinates on the unit circle when theta is pi over 10. This is not a special angle. It's not one we memorized. And we can breathe a sigh of relief because we have the word approximate. Now when I throw these questions out, usually students are stumped, but really this question should be a lot easier than all the other ones. Remember, this point on the unit circle is cos theta sine theta, and in this case cos pi over 10 and sine pi over 10. Again, this isn't a special angle, but again we only want the approximate value, so we use our calculator. And we get 0.95 approximately, rounded to 2 decimal places, and we get 0.31 approximately, and so the coordinates of this point are 0.95 and 0.31. Example 7, find the approximate values for each trig ratio to 3 decimal places. Approximate, we're going to use our calculator. 7 pi over 5 is not a special angle, neither is 5.9, neither is this one. So we're just going to use our calculators. Put this in our calculators. Now, make sure your calculator is in the right mode. This one is a radian measurement. This one is also radian. This one is degree mode. Or we need to be in degree mode. The first one, put that in our calculator, 3.078. Second one, put in our calculator, negative 0.374. And last one, put that in our calculator and change the mode of your calculator. So in this course, we have to be changing the mode constantly based on the question that we're doing. So put yourself in degree mode, 0.839. This was part of Trigonometry 3, solving problems using the 6 trigonometric ratios for angles expressed in radians and degrees. There's some questions, give them a try, see if you know what you are doing.